Hello everyone and welcome back. In this video we're going to be talking about the simple pendulum. Actually, there are many different types of pendulums. Three common examples are the physical pendulum, simple pendulum, and torsional pendulum. A physical pendulum is defined to be a rigid object, meaning that it has mass, that swings back and forth about a pivot point. An example of a physical pendulum is the swinging arm on a grandfather clock. The circle at the bottom has mass, and so does the pivoting arm. A simple pendulum, on the other hand, consists of a small object called a point mass or pendulum bob that hangs from a string with negligible mass. A torsional pendulum consists of a hanging mass suspended by a negligible string that instead of swinging back and forth, it instead twists back and forth around its central axis. And it's important to recognize there's different types of pendulums because each has a different equation to describe its motion. As a pendulum swings back and forth, it exhibits a sinusoidal motion, meaning that it maps out a sine or cosine wave. Here we can see the pendulum going back and forth, and if somebody was rolling this piece of paper, we could see that sine or cosine wave up here. This makes us wonder if a pendulum oscillates in simple harmonic motion. We learned in a previous lesson that if an object or system is in simple harmonic motion, there must be a restoring force present that aims to return the system to its equilibrium position. In addition, the restoring force must be proportional to the displacement and act in the opposite direction. So does a simple pendulum meet these conditions? Yes, it does. Let's look at this picture. When I displace the pendulum bob from its equilibrium position B and pull it to C, a restoring force does appear that aims to return the bob back to B. And yes, the restoring force is proportional to the displacement and acts in the opposite direction, just like a mass on a spring. But notice that the displacement x is now an angular displacement denoted by theta when we're talking about a pendulum. When a mass oscillates on a spring, the restoring force is equal to kx. With a pendulum, however, it's a bit more complex. So let's start by drawing a free body diagram of the pendulum bob when it's pulled to the side. The first force that acts on the bob is Fw, and I'm drawing that pointing straight down. And there's also tension in the string that we can label as Ft. And those are the only two forces that should be drawn on the free body diagram when the pendulum bob is at the side. So where's the restoring force? The restoring force turns out to be a component of Fw. So let's look at the drawing on the other side of the picture. Let's put in Fw, which is labeled mg in this picture, and Ft, which is labeled as capital T. You might recognize that this picture looks like the conical pendulum from circular motion. And just like the conical pendulum or an inclined plane, the weight vector can be broken down into an x and a y component. So theta on the top is equal to theta down here. This vector here is equal to mg cosine theta, and this vector is equal to mg sine theta. And if the bottom vector is mg sine theta, that means that the top vector is mg sine theta. And this top vector is the restoring force. So the restoring force in a simple pendulum is equal to mg sine theta. And this equation is in the same form as F equals kx. mg is a constant and sine theta is an angular displacement. Next, let's look at some facts about a simple pendulum and relationships that exist while oscillating. I exaggerated my picture a bit so it's easier to see. Let's start by noticing that when a pendulum swings back and forth, there's a difference in height. When it hangs straight down, it's at its equilibrium position, which the angular displacement is 0, so I wrote down theta equals 0, and h equals 0 in terms of its height. And then when it oscillates, it will swing up a distance h. When it's at position 3, you can see that we have formed a triangle here, where the hypotenuse is the length of the string, and if we use trig, we can find out that this segment here will be equal to L cosine theta. So from the picture, we can see that L cosine theta plus h must equal L, or the length of the string. This can be a helpful relationship to know when you're solving some problems. Next, let's look at the simple harmonic motion relationships that exist. So when the pendulum bob is at position 1, it's at its maximum angular displacement. And when we're at our maximum angular displacement, the restoring force is at a maximum and the acceleration's at a maximum. We also have our maximum potential energy as measured from h equals 0, and the kinetic energy 0, and the velocity of the pendulum bob is temporarily equal to 0. And the same thing is true when it swings over here to position 3. But as it swings back and forth from position 3 to 1, it's going to pass through equilibrium. At equilibrium, the restoring force is 0, the acceleration 0, the potential energy 0, and all of that potential energy from position 3 has now turned into kinetic energy, which means that the pendulum bob is moving fastest as it moves through its equilibrium position. This is similar to a mass on a spring. So let's look at an example related to energy. A 100-gram pendulum bob swings back and forth. Letter A says, if the pendulum bob reaches a maximum height of 40 centimeters above the ground, calculate the velocity of the mass as it passes equilibrium. So we can solve this problem easily by thinking about conservation of energy. So we know that at position 1, all of the energy is potential and we have no kinetic energy. So the potential energy is mgh, and we find out that the potential energy, which is also equal to the total energy of the system, is 0.392 joules. And now as the pendulum bob swings down to equilibrium, all of that potential energy is going to turn into kinetic energy. So the kinetic energy is 1/2 mv squared, so 0.392. The 1/2 I turned into a 0.5 times 0.1 v squared, and the velocity as it passes equilibrium is 2.8 meters per second. And that is the maximum velocity of the pendulum bob. I could have also solved the problem by recognizing that I have potential energy at position 1 that is going to all turn into kinetic energy at position 2, so mgh equals 1/2 mv squared, and that the mass actually cancels out, and then I could solve for the velocity. Part B says, determine the height of the mass when its velocity is 1.5 meters per second. So again, I'm going to solve this with a conservation of energy approach. So this time we know that the total energy is the sum of the potential plus the kinetic, and we know the total energy is 0.392 joules. So we know the kinetic energy is 1/2 mv squared, and again, the kinetic energy is not at a max. So I can then take the total energy minus the kinetic energy and solve for the potential, or solve for h in this equation, and we find out that h is 0.29 meters above h equals 0. The period of a simple pendulum is the time it takes to make one complete oscillation. In this example, that means going from point A to C and then back to A. You can also calculate the period using this equation. T equals 2 pi times the square root of L over G. So T is the period, L is the length of the string. Let's pause there for a second. When you measure the length of the string, you should always measure from the point of attachment to the center of mass of the pendulum bob to get good, accurate results. And then G is the acceleration due to gravity. I also just want to point out how similar this equation looks to the period of a mass on a spring. So in one equation we have an L over G, in the other one we have an M over K. Now that we know that the time it takes to go back and forth depends on the length of the string and the acceleration due to gravity, let's discuss what doesn't matter. You'll notice that the mass of the pendulum bob does not matter. And we know that because mass is not in the equation. In fact, in the derivation of the equation, the mass term cancels out. But if you're doing an experiment, you might want to make your pendulum bob as small as possible in order to minimize air resistance. Also, the amplitude of swing that's labeled theta does not matter. This again is a common misconception. It takes the same amount of time to go from point A to C as it does to swing from point X to Y. When deriving the equation for the period of the simple pendulum, the small angle approximation was used. The small angle approximation is a trig simplification that is sometimes used when theta is small. The small angle approximation says that if theta is small and measured in radians, then sine of theta is approximately equal to just theta itself. This means that the sine function was dropped in the derivation. Let's look at an example so you can see how this applies to a pendulum. So let's say that we took the pendulum bob and we pulled it off to the side 4 degrees. So let's now convert 4 degrees into radians. So 4 degrees, we have 360 degrees is 2 pi radians. So that turns out to be 0.0698 radians. So that's theta by itself. But what is sine theta? It's also 0.0698 radians. So because theta is approximately equal to sine theta, the sine function is sometimes dropped. And because the small angle approximation was used in deriving the period equation, it means that the equation only holds true for small angles. So then the question becomes, what is considered a small angle? Honestly, it's a bit subjective, but here's a chart that can maybe help us decide. So we just talked about 4 degrees, and even at 4 degrees, there is a difference between theta and sine of theta if we had kept more than 4 decimal places. So let's look at the chart and let's look at 14 degrees. So if we pulled the pendulum bob off to the side 14 degrees, we would end up with a theta in radians of 0.2443. And then sine of that value in radians is 0.2419. So already with 4 decimal places, we can see there's a difference in values. And that turned out to be a 1% difference or a 1% error. And then if we move up to 20 degrees, you can see that we're already at a 2% error. So there is no standard definition for a small angle. Sometimes you'll hear people say or you'll read that a pendulum amplitude should be less than 10 degrees or less than 15 degrees, etc. But now you know why people are making such statements. So if you're going to do a pendulum lab based on this equation, you're going to have to decide what theta to use and how much error you're willing to accept in your results, and that's in addition to any other error that's already present in the lab. And also remember, the greater the angle, the more that air resistance is going to come into play. So now that we understand the small angle approximation, let's look at the derivation for the period of a simple pendulum. So it says a simple pendulum of length L rotates about one end. Starting with Newton's second law in rotational form, derive the equation for the period of the pendulum in terms of given variables and fundamental constants. So it says that we are supposed to start with Newton's second law in rotational form. That's T equals I alpha. And let's start with T, torque. Torque is normally an F times L or an F times R. In this case, we have a point mass, and this is the axis of rotation. And so the torque would be equal to F times R, but the R is the distance from the point mass to the axis of rotation, which is going to be equal to the length of the string. So that's what that L stands for. And then we have a negative F. So that is the restoring force. So when we pull the pendulum off to the side, the restoring force acts in the opposite direction. So that's where the negative mg sine theta came from. So in the next step, I divided both sides of the equation by I, the rotational inertia, and end up with alpha equals negative mg sine theta L over the rotational inertia is that of a point mass. And so that is going to be an mr squared. And in this case, again, R is equal to L. So I wrote it as ml squared. So now we can cancel a few things. So I can cancel the two m's. I can cancel one of the L's in the denominator and the one in the numerator, and I then end up with negative g sine theta over L. This is where I'm going to apply the small angle approximation. So I'm going to say that I'm only going to pull my pendulum off to the side, small angles. So therefore, sine theta is approximately equal to just theta by itself. So for that reason, I now have sine theta, and I am just dropping the sine and making it theta. So I now have negative GL over theta. And I also know that since a pendulum oscillates in simple harmonic motion, that angular acceleration is equal to negative omega squared times the angular displacement. So I'm now going to set these two things equal to each other. And when I do that, I end up with, I have a theta here and a theta here, so I can cancel those. I can cancel the negative signs. I end up with omega squared equals g over L. And then I can take the square root of both sides. We know that omega is equal to 2 pi f, and frequency is 1 over t, so now I end up with 2 pi over t. So I'm going to put 2 pi over t in for omega, so I did that here, equals square root of gl. Now I'm just going to do some algebra and solve for t, and I end up with t equals 2 pi square root of L over g, which is the period for a simple pendulum. You should also be able to use the period of a simple pendulum equation to find the acceleration due to gravity at your location. Let's look at this example. After landing on the moon, an astronaut constructed a simple pendulum by tying a small weight to a piece of string 60 centimeters long. She then pulled the pendulum bob to the side and measured the time for 10 complete oscillations. If the total time was 38.2 seconds, what is the acceleration due to gravity on the moon? So we can start by writing down the simple pendulum equation, and we know that it took 38.2 seconds for 10 oscillations, which means that the time for one oscillation is 3.82. So now I just plugged in my values, 3.82, the length of the string I converted into meters, and I'm just going to solve for g. In doing my algebra, I chose to square everything and got an acceleration due to gravity of 1.62 meters per second squared on the moon. And if you're asked to design an experiment, you'll get better results if you use more than one data point. So how can we design an experiment that allows us to collect more data? Let's use the period of the pendulum equation to guide us. Since I'm trying to find the acceleration due to gravity, I'm going to want the g to be in the slope position when I line the equation up with y equals mx plus b. So you can see that I broke up this square root term and put square root of L on the top, square root of g on the bottom, and just slid it over a bit so it's in the slope position. Now I know that if I graph period on the y-axis and square root of L on the x-axis, the slope of the best fit line will be equal to 2 pi over square root of g. I can then just solve for g. And if you don't like square roots, you can also do the same thing by squaring all of the terms. And again, lining it up with y equals mx plus b. And I could also graph t squared on the y-axis and L on the x-axis. And now the slope of the best fit line will be equal to 4 pi squared over g. Either way, you'll get a linear graph that you can use to find the acceleration due to gravity.